we're going to drift into a question so profound, so quietly mind-bending that it has puzzled the greatest minds in physics for generations. What existed before the very first moment? What was there before the Big Bang? How can we even conceive of a time before time itself began? In this exploration, we'll journey to the very edge of scientific understanding, where mathematics meets mystery and where our most sophisticated theories dissolve into wonder. But before we begin, feel free to comment your time and location below. There's something beautifully humbling about contemplating the ultimate origin while scattered across our small planet, each of us under the same ancient sky that has witnessed every moment of cosmic history. The visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination drift through the deepest mysteries of existence. I would love for you to stay with me until the end, to explore these profound ideas together. But there's absolutely no problem if you doze off along the way. Let your thoughts float across the vast ocean of possibility. Let's begin. Welcome to a journey that takes us beyond the beginning itself, before the first star ever flickered to life in the cosmic darkness. Tonight, we're exploring one of the most profound questions humanity has ever dared to ask. What existed before the Big Bang? It's a question that pushes against the very boundaries of science, philosophy, and imagination, taking us to the edge of everything we think we know about the nature of existence. As you settle into this moment of quiet contemplation, perhaps with the gentle weight of evening settling around you, consider that we're about to explore territory where even time itself becomes questionable. The story we're about to unfold challenges everything we typically think about beginnings and endings, about cause and effect, about the very nature of reality itself. For most of human history, this question had a simple answer. Some eternal deity set everything in motion. Even Isaac Newton believed that God created the universe just a few thousand years ago. The answer was straightforward, wrapped in religious certainty, and requiring no further investigation. But as our understanding of the cosmos evolved, so did the complexity of our questions. Later, many scientists, including a young Albert Einstein, assumed the universe itself to be eternal and everlasting, no beginning, no end, just an infinite expanse of space and time, stretching in all directions forever. This too seemed to solve the problem neatly. If the universe had always existed, there was no need to explain what came before it. But then came a discovery that changed everything. In the early 20th century, astronomers began to notice something extraordinary about distant galaxies. They were moving away from us, not just a few of them, but all of them. And the farther away they were, the faster they seemed to be receding. The universe wasn't static and eternal after all. It was expanding. This observation led to a revolutionary insight. If the universe is expanding now, it must have been smaller in the past, much smaller. And if we trace this expansion backward through time, we arrive at a moment when everything we can observe was compressed into an unimaginably small, dense, and hot point. This was the birth of Big Bang cosmology, and with it came a profound new mystery. If the universe began in this cosmic explosion of space and time, what existed before that moment? The question seems natural enough. After all, everything in our experience has a cause, a predecessor, something that came before it. But here we encounter one of the most fundamental puzzles in all of science. According to our best current theory, Einstein's general relativity, space and time themselves, began at the Big Bang. There was no before, because time itself didn't exist yet. Asking what came before the Big Bang, some argued, is like asking what lies north of the North Pole. The question contains its own impossibility. Yet this answer, elegant though it may be, has never fully satisfied the human mind. We are pattern-seeking creatures, storytellers by nature, always attempting to weave the disparate threads of experience into coherent narratives. The idea that the universe might simply have popped into existence from nothing, with no cause, no predecessor, no deeper explanation, feels unsatisfying at the deepest level, and so physicists began to probe deeper, to push beyond the apparent barrier of the Big Bang itself. What they discovered in their mathematical explorations is that the question of what came before may not be meaningless after all. In fact, it may be one of the most important questions we can ask about the nature of reality. The first hint that something might have preceded the Big Bang came from a curious problem in cosmology. When astronomers looked at the cosmic microwave background radiation, the afterglow of the Big Bang itself, they found something puzzling. The temperature of this ancient light was remarkably uniform across the entire sky. Too uniform, in fact, to be explained by standard Big Bang theory. Here's the puzzle. Light travels at a finite speed, and the universe has a finite age. This means there are regions of the cosmos that are so far apart that light from one could never have reached the other in the time since the Big Bang. These regions should have no way of knowing about each other's existence, let alone coordinating their temperatures. And yet, when we measure the cosmic background radiation, we find that these causally disconnected regions have almost exactly the same temperature. It's as if you walked into a vast auditorium where no one could communicate with anyone else, and yet everyone was humming the same tune in perfect harmony. How could this be possible? The solution to this puzzle led physicists to propose something extraordinary. What if the Big Bang wasn't actually the beginning of everything, but rather a transition from one state of the universe to another? What if there was a period before the Big Bang when different regions of the cosmos could communicate with each other, establishing the uniform conditions we observe today? This insight gave birth to the theory of cosmic inflation, one of the most successful and revolutionary ideas in modern cosmology. According to this theory, before the hot, dense state we call the Big Bang, the universe underwent a period of incredibly rapid expansion. In less than a trillionth of a trillionth of a trillionth of a second, space itself expanded by an enormous factor, stretching tiny quantum fluctuations to cosmic scales. But here's what makes this truly remarkable. This inflationary period happened before the Big Bang. It represents a genuine pre-Big Bang era, a time when the universe existed in a completely different state than anything we observe today. During inflation, the universe was cold, nearly empty, and expanding at a rate that dwarfs even our current cosmic expansion. Imagine space itself as a balloon being inflated at an incredible rate. Any wrinkles or irregularities on the balloon's surface would be stretched smooth by this rapid expansion. Similarly, cosmic inflation would have stretched any initial irregularities in the early universe to enormous scales, leaving behind the smooth, uniform cosmos we observe today. But inflation does more than just solve the uniformity problem. It provides a mechanism for understanding how the Big Bang itself came to be. As this period of rapid expansion came to an end, The energy driving inflation didn't simply disappear. Instead, it underwent a remarkable transformation, converting into the matter and radiation that filled the universe with the super-hot plasma of the Big Bang. This metamorphosis flooded space with particles and energy, creating the conditions we associate with the cosmic origin story. The Big Bang, in this view, wasn't the beginning of everything, but rather the end of inflation and the beginning of the universe's more familiar evolution. Yet even this remarkable insight raises new questions. If inflation preceded the Big Bang, what caused inflation itself? What determined when it would begin and end? And perhaps most intriguingly, could inflation be an ongoing process, creating not just our universe but countless others? This last question leads us into truly mind-bending territory. Some versions of inflation theory suggest that while inflation ended in our region of space, it continues elsewhere, eternally creating new expanding regions that become universes in their own right. This eternal inflation would mean that our Big Bang was just one bubble forming in an infinite cosmic ocean, with new bubbles constantly appearing throughout a vast multiverse. The implications are staggering. If eternal inflation is correct, then asking what came before our Big Bang is like asking about the weather in a distant country. There was no single before, but rather an ongoing process of cosmic creation that has been happening forever and will continue indefinitely. But inflation is not the only theoretical framework that attempts to address the pre-Big Bang mystery. Another approach emerges from quantum gravity, the attempt to understand how gravity behaves at the smallest scales where quantum effects become important. According to some quantum theories of gravity, the Big Bang singularity where density and temperature become infinite is not physically real, but rather represents the breakdown of our current theories. When quantum effects are properly included, the singularity might be replaced by something called a quantum bounce. In this scenario, our expanding universe emerged not from a singular point, but from the collapse and subsequent rebound of a previous universe, like a cosmic rubber ball that contracts to a minimum size before expanding again. The universe might undergo cycles of contraction and expansion, with each Big Bang representing not a true beginning, but a transition point in an eternal cosmic rhythm. This bouncing universe model suggests that before our Big Bang, there was an entire cosmos contracting under its own gravity. As this previous universe shrank, quantum effects eventually became strong enough to halt the collapse and reverse it into expansion. Our Big Bang would then represent the moment when this quantum bounce occurred, launching our universe on its current expanding trajectory. The mathematics of these quantum bounce models are extraordinarily complex, involving theories that merge general relativity with quantum mechanics in ways that push the boundaries of current physics. Yet they offer a compelling vision of a cosmos that has no beginning and no end, only an eternal dance of contraction and expansion, driven by the fundamental forces of nature. As we drift deeper into these theoretical waters, we begin to see that the question of what came before the Big Bang opens onto vistas of possibility that dwarf our everyday experience. Whether through eternal inflation, quantum bounces, or other exotic mechanisms, modern physics suggests that our universe may be part of something far grander and more mysterious than we ever imagined. But these theories also reveal something profound about the nature of scientific inquiry itself. The question of cosmic origins pushes us to the very limits of what can be known, tested, and verified. we find ourselves constructing elaborate mathematical frameworks to describe conditions so extreme that they may forever remain beyond direct observation. Yet in this pushing against the boundaries of knowledge, we discover not just new theories about the cosmos, but new insights into the nature of existence itself. The universe reveals itself to be stranger, more beautiful, and more mysterious than our ancestors could have conceived. These cosmic theories also force us to confront a fundamental question about the nature of reality itself. When we speak of what came before the Big Bang, we're not just asking about events in the distant past. We're probing the very foundations of existence, questioning whether our most basic concepts of time, space, and causation have any meaning at the deepest levels of reality. Consider for a moment the strange implications of some of these pre-Big Bang scenarios. If our universe emerged from an eternally inflating multiverse, then the very concept of a unique beginning becomes meaningless. There would be no single moment of creation, no first cause, no ultimate origin story. Instead, we would find ourselves in an endless sea of cosmic generation, where universes bubble into existence like foam on an infinite ocean. This vision challenges something fundamental about how we understand stories and meaning. We are creatures who think in terms of narratives with clear beginnings, middles, and ends. But the multiverse offers us something radically different, a reality where every possible story is being told simultaneously, where every beginning is preceded by another beginning, stretching back through an infinite regress of cosmic creation. Yet even within this apparent chaos, patterns emerge. The laws of physics that govern our universe appear to be remarkably fine-tuned for the emergence of complexity and life change, any one of several fundamental constants by even a tiny amount, and stars might never form. Atoms might never bind together, or the universe might collapse before anything interesting could happen. This fine-tuning puzzle becomes even more mysterious when we consider pre-Big Bang cosmology. If our universe is just one bubble in an eternal multiverse, why do we find ourselves in a region where the physical laws allow for such rich complexity? Is this simply a selection effect, where we can only exist in universes capable of supporting observers? Or does it hint at some deeper organizing principle governing the creation of cosmic domains? Some theorists have proposed that the pre-Big Bang state might have been far simpler than our current universe, with complexity emerging only gradually through a series of phase transitions and symmetry breakings. In this view, the apparent fine-tuning of our physical laws might be the natural result of cosmic evolution, rather than an unlikely coincidence requiring explanation. But other approaches to pre-Big Bang physics suggest even more radical possibilities. String theory, our most ambitious attempt to unify all the fundamental forces of nature, envisions a reality with far more dimensions than the three of space and one of time that we experience directly. In this higher dimensional framework, our entire universe might exist as a membrane floating in a vast extra-dimensional space. According to some string theoretic scenarios, known as ekpyrotic models, our Big Bang might have resulted from a collision between such membranes in this higher dimensional realm. Two cosmic brains, each carrying its own three-dimensional space, would slowly approach each other through the extra dimensions, eventually colliding in a cataclysmic event that we experience as the Big Bang. This collision wouldn't be a one-time event, but rather part of an eternal cycle. The brains would approach, collide, bounce apart, and then slowly drift back together for another collision. Each collision would generate the hot, dense conditions of a Big Bang, while the periods between collisions would represent eras of cosmic contraction and cooling. The mathematical beauty of these ekpyrotic models lies in their ability to explain many puzzling features of our universe without requiring the extreme conditions traditionally associated with the Big Bang singularity. Instead of everything emerging from a point of infinite density, the collision between brains creates finite but extreme conditions that naturally evolve into the expanding cosmos we observe. Yet perhaps the most mind-bending aspect of these theories is how they challenge our understanding of identity and uniqueness. If the universe undergoes eternal cycles of collision and expansion, or if it emerges from an eternally inflating multiverse, then the question of what makes our cosmic epoch special becomes deeply puzzling. Are we living in the first iteration of cosmic evolution, or have there been countless cycles before us? If the universe bounces eternally between expansion and contraction, could there have been previous versions of ourselves living in earlier cosmic cycles, asking the same questions we're asking now? The mathematics of these cyclical models suggests that while the overall pattern might repeat, the details could be different each time, like variations on an infinite cosmic theme. These questions push us toward a profound philosophical territory where science meets the deepest puzzles of existence. What does it mean for something to exist if it's part of an infinite ensemble of possibilities? How do we understand our place in reality if that reality consists of endless repetitions and variations of cosmic evolution? Some physicists have suggested that these questions might be fundamentally unanswerable, not because of limitations in our knowledge or technology, but because they probe beyond the boundaries of what can meaningfully be asked. Just as asking what lies north of the North Pole reveals the limits of directional concepts, asking about our uniqueness in an infinite multiverse might reveal the limits of concepts like identity and significance. But this apparent limitation might actually point towards something profound about the nature of consciousness and observation. If the multiverse contains infinite variations and possibilities, then the fact that we find ourselves in a region capable of supporting complex structures and conscious observers becomes not a puzzle to be solved, but a fundamental feature of how reality is structured. This observer-dependent aspect of cosmology introduces elements that feel almost mystical in their implications. The universe we observe might be shaped not just by physical laws and initial conditions, but by the very fact that we are here to observe it. This doesn't mean that consciousness literally creates reality, but rather that the act of observation selects which branch of infinite possibilities we experience. Recent developments in pre-Big Bang cosmology have begun to explore these observer effects more rigorously. Some models suggest that the pre-Big Bang state might have contained quantum information that influences not just the physical evolution of the universe, but also the emergence of observers capable of questioning their own origins. These theories venture into territory where physics, philosophy, and even theology begin to converge. If the pre-Big Bang state contained the seeds of consciousness and observation, then the question of what existed before the Big Bang becomes intimately connected with the question of why anything exists at all. The answers emerging from these investigations are not the simple, definitive explanations that we might hope for. Instead, they reveal a reality far stranger and more wonderful than our ancestors imagined. A cosmos where beginning and ending lose their conventional meanings, where causation becomes circular or infinite, where observation and reality interweave in ways that challenge our deepest assumptions about existence. As we continue our journey through these cosmic mysteries, we begin to see that the question of what came before the Big Bang is really many questions disguised as one. It's a question about time and causation, about uniqueness and repetition, about the role of consciousness in a quantum cosmos, and ultimately about what it means for anything to exist at all. The theoretical frameworks we've explored, from eternal inflation to quantum bounces to colliding brains, each offer glimpses into this deeper mystery. They suggest that reality might be far more vast, complex and beautiful than we ever dared imagine. But they also remind us that some questions might be too profound for any finite mind to fully grasp. Perhaps this is as it should be. In a universe capable of giving rise to consciousness and wonder, maybe the deepest questions should remain open, forever inviting us to push further into the mystery. The question of what came before the Big Bang might not have a final answer, but in asking it, we participate in something magnificent. The universe's attempt to understand itself through the curious minds it has somehow managed to create. But there's another pathway into these pre-Big Bang mysteries that leads us through some of the most elegant mathematics in all of physics. It emerges from our growing understanding of something called loop quantum gravity, a theoretical framework that attempts to describe the very fabric of space-time at the smallest possible scales. To understand this approach, imagine zooming into reality with a microscope of impossible power. As you peer deeper and deeper into the structure of space itself, classical physics tells us that you should be able to keep zooming forever, finding smaller and smaller divisions of distance and time. But loop quantum gravity suggests something radically different. At the tiniest scales, space and time themselves become granular, made up of discrete units that cannot be divided further. This quantum granularity of space-time has profound implications for our understanding of cosmic origins. When we trace the expansion of the universe backward using classical physics, we eventually reach a point where the mathematics breaks down completely. The equations predict infinite density, infinite temperature, infinite curvature of space-time itself. These infinities signal not physical reality, but the failure of our theoretical tools. But when quantum effects are properly included, something remarkable happens. The infinite compression that classical physics predicts is prevented by the discrete nature of space and time at quantum scales. Just as matter cannot be compressed beyond the size of atoms without triggering nuclear reactions, space-time itself cannot be compressed beyond the Planck scale without triggering quantum geometric effects that fundamentally alter the physics. This quantum resistance to infinite compression suggests that the Big Bang wasn't a singular event emerging from nothing, but rather a quantum bounce emerging from something. In this picture, our expanding universe arose not from a point of infinite density, but from a previous universe that had contracted to the minimum size allowed by quantum geometry before rebounding into expansion. The mathematics of this quantum bounce are breathtakingly elegant. They describe a cosmos that breathes in cosmic rhythms, contracting and expanding in cycles that could stretch across unimaginable spans of time. Each contraction would compress matter and energy to the quantum limit, triggering a bounce that launches a new phase of expansion. Our Big Bang would represent just one breath in this eternal cosmic respiration. What makes this scenario particularly compelling is how it resolves many of the puzzles that have long plagued cosmology. The uniformity of the cosmic microwave background, the flatness of space, the particular mix of matter and energy we observe, all emerge naturally from the dynamics of the quantum bounce without requiring special initial conditions or fine-tuning. But perhaps most remarkably, this bouncing cosmos offers a vision of time that is both finite and infinite. Each individual cycle has a beginning and end, a contraction phase followed by expansion, yet the sequence of cycles extends infinitely in both directions, with no first bounce and no final collapse. Time becomes not a line with a starting point, but a spiral, stretching endlessly through the dimensions of possibility. This cyclical view of cosmic evolution raises profound questions about memory and information. If the universe undergoes repeated cycles of contraction and expansion, what happens to the information accumulated during each cycle? Do the details of stars and galaxies, of life and consciousness, survive the quantum bounce to influence the next cosmic epoch? Recent research suggests that while most information might be scrambled during the extreme conditions of the bounce, certain quantum signatures could persist from cycle to cycle. These remnant patterns might influence the initial conditions of each new universe, creating a kind of cosmic memory that connects one cycle to the next. In this view, our current universe might carry within its deepest structure the faint echoes of countless previous cosmic incarnations. Yet even as these quantum theories of cosmic cycling become more sophisticated, they point toward an even deeper mystery. What determines the overall rhythm of these cosmic cycles? What sets the timescale for contraction and expansion? And perhaps most puzzling of all, why does the universe seem to follow mathematical laws that allow for such elegant cyclical behavior? These questions lead us into territory where physics begins to merge with philosophy in ways that would have been unimaginable to earlier generations of scientists. The quest to understand what came before the Big Bang has evolved into an exploration of the deepest principles governing reality itself. Some theorists have begun to explore the possibility that the laws of physics themselves might evolve from cycle to cycle, undergoing subtle changes during each quantum bounce. In this view, the fundamental constants that govern the strength of forces and the masses of particles might not be truly constant, but rather variables that drift slowly across cosmic time. This evolutionary cosmology suggests that our universe might be just one experiment in an endless series of cosmic trials, each testing different combinations of physical laws and initial conditions. Most of these experiments might produce sterile universes, incapable of generating complexity or life. But occasionally, as in our case, the parameters might align in ways that allow for the emergence of stars, planets, and conscious observers. The implications of this perspective are simultaneously humbling and inspiring. If the laws of physics can evolve, then our universe represents not just a random configuration of matter and energy, but a cosmic achievement, a rare success story in the ongoing experimentation of reality itself. We exist not despite the apparent fine-tuning of physical constants, but because of an evolutionary process that has gradually optimized the universe for complexity and consciousness. But this raises an even deeper puzzle. What drives this cosmic evolution? What selects for universes capable of generating observers? Some theorists have proposed that consciousness itself might play a role in cosmic evolution, not through any mystical influence, but through the fundamental quantum mechanical connection between observation and reality. In quantum mechanics, the act of measurement plays a crucial role in determining which of many possible states becomes actual. Some interpretations suggest that conscious observers are necessary to collapse quantum possibilities into definite outcomes. If this is correct, then universes capable of generating observers might have a selective advantage in the cosmic evolutionary process. This observer participatory universe represents one of the most radical ideas in modern cosmology. It suggests that the question of what came before the Big Bang is intimately connected with the question of why there are beings capable of asking such questions. The pre-Big Bang state might have been not just a physical condition, but an information-rich environment containing the quantum seeds of consciousness itself. Yet even as we explore these exotic possibilities, we must remain grounded in the recognition that much of this territory remains highly speculative. The conditions that existed before the Big Bang, if indeed anything existed, are so far removed from anything we can directly observe that our theories venture into realms where mathematics and imagination begin to merge. This doesn't make these investigations any less valuable or meaningful. Throughout the history of science, our most important breakthroughs have come from pushing beyond the boundaries of the directly observable, using mathematics and theoretical reasoning to explore realms that our senses cannot reach. The theories of atoms, of electromagnetic fields, of curved space-time, all emerged from such theoretical adventures long before they could be directly confirmed. The quest to understand pre-Big Bang physics represents the latest chapter in this ongoing adventure of human curiosity. It takes us to the very edges of what minds like ours can conceive, to territories where the familiar concepts of time, space, and causation begin to dissolve into something far stranger and more wonderful. As we journey deeper into these mysteries, we begin to appreciate that the question of what came before the Big Bang might be unanswerable, not because it's too difficult, but because it transcends the very categories through which we must think about reality. Like ancient philosophers contemplating infinity or mathematicians grappling with paradoxes of self-reference, we find ourselves pushing against the fundamental limits of conceptual thought itself. But perhaps this is precisely what makes the inquiry so profound and valuable. In pushing against these limits, we discover not just new theories about the cosmos, but new possibilities for consciousness itself. We stretch our minds to accommodate concepts that would have been literally unthinkable to previous generations, expanding the horizon of what it means to be a conscious observer in a mysterious universe. The various theoretical frameworks we've explored, from eternal inflation to quantum bounces to cyclical evolution, each represent different attempts to extend our understanding beyond the apparent barrier of the Big Bang. They offer us glimpses into possible pre-Big Bang realities, each stranger and more wonderful than our everyday experience would suggest. Yet perhaps the most important insight emerging from these investigations is not any particular theory about what came before the Big Bang, but rather a deeper appreciation for the profound mystery of existence itself. The fact that anything exists at all, that there are laws of physics, that consciousness can emerge from matter and contemplate its own origins, remains perhaps the deepest puzzle of all. Whether our universe emerged from eternal inflation, quantum bounces, colliding brains, or some other exotic mechanism we haven't yet imagined, the fundamental question of why there is something rather than nothing continues to hover at the edges of our understanding. This question might be unanswerable in principle, not because of limitations in our knowledge, but because it probes the very foundations upon which all knowledge must rest. In this sense, the quest to understand what came before the Big Bang becomes not just a scientific investigation, but a kind of cosmic meditation, an attempt to touch the deepest mysteries of existence through the tools of mathematics and reason. We find ourselves using the universe's own capacity for self-awareness to probe the origins of that capacity, creating a strange loop of investigation that mirrors the cyclical cosmologies we've been exploring. As we continue this journey into the unknown, we carry with us the recognition that we are part of the very mystery we're trying to solve. We are arrangements of matter and energy that have somehow learned to ask questions about matter and energy. We are temporary patterns in the cosmic dance that have developed the ability to contemplate the choreography of that dance. This participatory aspect of cosmic investigation adds layers of meaning to our inquiry that extend far beyond the purely scientific. When we ask what came before the Big Bang, we're not just seeking information about distant events. We're participating in the universe's ongoing attempt to understand itself, to make sense of its own existence through the curious minds it has somehow managed to create. The mathematics that describe these pre-Big Bang scenarios are staggeringly complex, involving equations that stretch our understanding to its breaking point. Yet within these mathematical frameworks, patterns emerge that suggest something profound about the nature of reality itself. The quantum fields that might have given birth to our universe operate according to principles so subtle that they challenge our most basic assumptions about what it means for something to exist. Consider the quantum vacuum, that mysterious state that physicists sometimes describe as empty space. But emptiness, it turns out, is far more complex than we might imagine. Even in the absence of matter and energy, quantum fields continue to fluctuate, creating temporary particles that pop into existence and vanish again in timeframes so brief they defy our everyday understanding of permanence. These quantum fluctuations might hold the key to understanding cosmic origins. Some theories suggest that our entire universe began as just such a fluctuation, a random bubble of energy that happened to expand rather than collapse back into the vacuum. If this is correct, then the pre-Big Bang state wasn't nothing at all, but rather a seething ocean of quantum possibility from which universes occasionally emerge like waves cresting on an infinite shore. But this raises questions that probe even deeper into the mystery of existence. What governs these quantum fluctuations? What determines which possibilities become actual and which remain forever unrealized? The mathematics suggests that reality operates according to probability rather than certainty, with outcomes determined by cosmic dice rolls at the most fundamental level. This probabilistic nature of quantum reality has led some physicists to propose that all possible universes actually exist simultaneously, branching off from every quantum decision point into parallel realities that never intersect. In this many worlds interpretation, the question of what came before our Big Bang becomes even more complex, as our cosmic history represents just one thread in an infinite tapestry of parallel possibilities. The implications stretch the imagination beyond its normal limits. If every quantum possibility spawns its own universe, then there might be versions of reality where the Big Bang never occurred, where different physical laws govern the behavior of matter and energy, where consciousness evolved along completely different pathways, or perhaps never emerged at all. Yet even within this vast ensemble of possibilities, certain patterns seem to persist. The mathematical relationships that describe quantum behavior, the geometric principles that govern the curvature of space-time, the deep symmetries that connect different aspects of physical reality, all appear to transcend any particular universe or cosmic epoch. This suggests that the pre-Big Bang state, whatever it was, operated according to mathematical principles that exist in some sense independently of physical reality. The laws of mathematics don't depend on the existence of matter or energy or even space and time. They represent pure relationships, abstract patterns that somehow have the power to give rise to concrete physical existence. Some philosophers and physicists have argued that mathematics itself might be the ultimate reality, with physical universes emerging as particular solutions to abstract mathematical equations. In this view, the question of what came before the Big Bang becomes a question about the relationship between mathematical possibility and physical actuality. But mathematics, for all its power and elegance, cannot tell us why any particular set of equations should be instantiated in physical reality. Why should the abstract relationships described by quantum field theory or general relativity have any connection to actual events in spacetime? This remains one of the deepest mysteries in all of science and philosophy. The search for answers has led researchers to explore increasingly exotic theoretical territories. String theory, with its vision of reality as composed of tiny vibrating filaments in higher dimensional spaces, suggests that our familiar 3 dimensions of space and one of time might be just a shadow cast by a far more complex underlying structure. In these higher dimensional frameworks, our Big Bang might represent not the origin of everything, but merely a local event within a vast cosmic landscape where different regions operate according to different physical laws. The pre-Big Bang state might have been a period when our 3-dimensional slice of this higher reality was still connected to regions with radically different properties. Some string theorists have proposed that cosmic collisions in these higher dimensions could account for the periodic creation of universes like ours. Imagine vast membranes floating in hyperspace, occasionally intersecting in events that generate the extreme conditions we associate with the Big Bang. Each collision would create a new expanding universe, while the membranes themselves continue their eternal dance through dimensions we cannot directly perceive. These brain collision models offer a particularly elegant solution to the question of cosmic origins because they remove the need for a true beginning. The membranes themselves might be eternal, with collisions occurring at regular or random intervals throughout an infinite span of higher dimensional time. Our Big Bang would represent just one such collision in an endless series stretching both forward and backward through hypertime. Yet the more we explore these exotic scenarios, the more we confront a fundamental limitation in our ability to understand ultimate origins. Every theory we construct, no matter how sophisticated, seems to push the mystery back one level without truly resolving it. If our universe emerged from quantum fluctuations, what created the quantum fields? If it arose from colliding brains, what determines the dynamics of those brains? If it represents one branch in an infinite multiverse, what governs the branching process itself? This infinite regress suggests that the question of absolute origins might be fundamentally unanswerable, not because of limitations in our current knowledge, but because of deeper logical constraints on what can be explained every explanation requires assumptions, initial conditions, background laws, or principles that themselves remain unexplained. The quest for a complete understanding of cosmic origins might be chasing something that cannot exist in principle. But this apparent limitation doesn't diminish the value of our investigations. In pushing against the boundaries of explanation, we discover profound truths about the nature of existence and our place within it. We learn that reality is far stranger and more wonderful than common sense would suggest, operating according to principles that challenge our deepest intuitions about time, space, and causation. The various pre-Big Bang scenarios we've explored each offer unique insights into these deeper patterns. Eternal inflation reveals how cosmic evolution can be both finite locally and infinite globally, with each universe representing a temporary island of expansion in an ocean of ongoing cosmic generation. Quantum bounce models show how apparent endings can transform into new beginnings, with death and birth intimately connected in cosmic cycles that transcend individual existence. Higher dimensional collision scenarios demonstrate how our familiar reality might be embedded within structures so vast and complex that we can barely begin to imagine them. And multiverse theories suggest that our particular combination of physical laws and initial conditions represents just one note in an infinite cosmic symphony where every possible melody is being played simultaneously. Each of these frameworks requires us to expand our conception of what it means for something to exist. We must learn to think about realities that extend beyond space and time as we know them, about mathematical structures that exist independently of physical instantiation, about infinite ensembles of possibilities where every conceivable variation is realized somewhere. This expansion of our conceptual horizons represents perhaps the most valuable outcome of pre-Big Bang research, regardless of which particular theory eventually proves correct. The investigation itself transforms our understanding of existence in ways that ripple through every aspect of human thought and culture. We begin to see ourselves not as isolated accidents in a hostile universe, but as integral participants in cosmic processes that connect the smallest quantum scales to the largest cosmic structures. Our capacity for consciousness and curiosity emerges not as an inexplicable anomaly, but as a natural consequence of the universe's inherent tendency toward increasing complexity and self-organization. This perspective suggests that the question of what came before the Big Bang is intimately connected with the emergence of beings capable of asking such questions. The pre-Big Bang state, whatever it was, contained within its quantum structure the seeds of consciousness and inquiry that would eventually flower into minds like ours, capable of contemplating their own cosmic origins. The recursive nature of this situation creates a strange loop, where the investigation of cosmic origins becomes part of the cosmic story itself. We are the universe investigating its own beginnings, temporary arrangements of matter and energy that have achieved the remarkable capacity for self-reflection and cosmic contemplation. This self-referential aspect of cosmological inquiry adds layers of meaning that extend far beyond the purely scientific. When we study the cosmos, we participate in the universe's ongoing process of self-discovery. Every equation we solve, every theory we develop, every insight we achieve represents the cosmos coming to know itself through the conscious minds it has somehow managed to create. The implications extend into realms that earlier generations would have considered purely philosophical or even spiritual. If consciousness represents a fundamental feature of cosmic evolution, rather than an accidental byproduct, then questions about the meaning and purpose of existence take on new dimensions. We might be not just observers of cosmic evolution, but active participants in the universe's journey toward greater complexity and self-understanding. Yet even as we explore these profound connections between consciousness and cosmos, we must remain humble about the limits of our understanding. The question of what came before the Big Bang probes territories so far beyond direct experience that our theories necessarily venture into realms where mathematics and metaphysics begin to merge. This doesn't invalidate our investigations, but rather highlights their unique character. We find ourselves using the tools of science to explore questions that philosophers and mystics have contemplated for millennia. The boundary between empirical investigation and speculative philosophy becomes increasingly blurred as we push toward the ultimate foundations of existence. Perhaps this blurring of boundaries is itself significant. The deepest questions about reality might require approaches that transcend traditional disciplinary divisions, combining mathematical rigor with philosophical insight, scientific methodology with imaginative speculation, empirical observation with theoretical boldness. The quest to understand what came before the Big Bang exemplifies this kind of boundary-crossing inquiry. It requires us to be simultaneously rigorous scientists and bold philosophers, careful mathematicians and imaginative storytellers. We must construct theories precise enough to make testable predictions, while remaining open to possibilities so exotic that they challenge our fundamental assumptions about the nature of existence. As we continue this extraordinary journey of discovery, we carry with us the recognition that we are exploring not just the cosmos, but the deepest capacities of consciousness itself. Every insight we achieve expands not only our knowledge of the universe, but our understanding of what it means to be conscious observers within that universe. The question of what came before the Big Bang thus becomes a mirror reflecting our own nature as conscious beings embedded in a mysterious cosmos. In seeking to understand cosmic origins, we simultaneously explore the origins of our capacity to seek such understanding. The investigation becomes a cosmic dialogue between mind and reality, between the universe's capacity for self-awareness and its drive towards self-comprehension. This cosmic dialogue reveals something profound about the nature of investigation itself. When we peer into the pre-Big Bang realm, we're not just collecting data about distant events. We're participating in a process that connects the deepest structures of reality with the emergence of minds capable of contemplating those structures. Every mathematical equation we derive, every theoretical model we construct, represents the universe using its own evolved complexity to investigate its origins. But as we venture deeper into these mysteries, we encounter theoretical frameworks that stretch our imagination to its breaking point. Consider the possibility that our universe emerged not from a single pre-Big Bang state, but from something far more exotic. A quantum superposition of all possible pre-Big Bang conditions simultaneously. In quantum mechanics, particles can exist in multiple states at once, until observation collapses them into definite configurations. Some cosmologists have proposed that the pre-Big Bang realm operated according to similar principles, but on a cosmic scale. Before observation, before the emergence of conscious beings, the early universe might have existed in a superposition of every conceivable initial condition. This quantum cosmological superposition would mean that asking what specific state existed before the Big Bang is fundamentally meaningless. There was no single state, but rather a ghostly ensemble of all possibilities, each weighted by quantum probability, amplitudes that we can calculate but never directly observe. The Big Bang itself might have represented a cosmic measurement event, collapsing this superposition into the particular universe we now inhabit. The mathematics of such quantum superposition cosmologies are breathtakingly elegant and utterly mind-bending. They describe realities where causation becomes probabilistic rather than deterministic, where the past remains fluid until observed, where the very notion of a definite history dissolves into quantum foam. Yet within this apparent chaos, statistical patterns emerge that match our observations with remarkable precision. These quantum approaches to pre-Big Bang physics connect with some of the strangest discoveries in modern physics. Experiments have confirmed that quantum entanglement can create instantaneous correlations between particles separated by vast distances. Some theorists have proposed that the pre-Big Bang state might have been characterized by cosmic entanglement, with different regions of the nascent universe connected by quantum correlations that transcended the normal limitations of space and time. If such cosmic entanglement existed, it could explain the remarkable uniformity we observe in the cosmic microwave background without requiring the rapid expansion of inflation. Different regions of the universe would share quantum states, not because they were once in causal contact, but because they emerged from an entangled pre-Big Bang condition where local properties were correlated across arbitrary distances. But quantum entanglement in the pre-Big Bang era raises puzzling questions about the nature of information and memory in cosmic evolution. If the early universe was characterized by quantum superposition and entanglement, what happened to that quantum information as the cosmos evolved? Did it disappear, or does it remain encoded somehow in the structure of space and time? Recent research suggests that quantum information might be more resilient than previously thought. Even in the extreme conditions of black holes, where matter and energy are crushed to unimaginable densities, quantum information appears to be preserved in subtle correlations that persist even after the black hole evaporates. This discovery has profound implications for our understanding of pre-Big Bang physics. If quantum information cannot be destroyed even in black holes, then the information present in the pre-Big Bang state might still exist somewhere in our current universe, encoded in ways so subtle that we haven't yet learned to detect them. The cosmic microwave background, the large-scale structure of galaxies, even the quantum vacuum itself might carry encrypted messages from the pre-Big Bang era, waiting for sufficiently clever minds to decode them. This possibility transforms our understanding of cosmic archaeology. Just as paleontologists reconstruct ancient life from fossil traces, cosmic archaeologists might eventually learn to reconstruct pre-Big Bang physics from quantum fossils embedded in the structure of contemporary reality. Every particle interaction, every gravitational wave, every fluctuation in quantum fields might preserve fragments of information about the conditions that preceded our cosmic genesis. The search for these quantum fossils represents one of the most ambitious scientific programs ever conceived. It requires developing mathematical tools capable of extracting ancient signals from the overwhelming complexity of current cosmic evolution. Researchers are exploring whether sophisticated pattern recognition algorithms, perhaps enhanced by artificial intelligence, might be able to identify pre-Big Bang signatures in vast datasets from cosmic observations. But as we develop these extraordinary investigative capabilities, we must also confront fundamental questions about the nature of cosmic memory itself. If information about pre-Big Bang conditions is preserved in current observations, does this mean that the past exists in some objective sense? Or does it suggest that the past is continually reconstructed by present observations, making cosmic history as much about current interpretation as ancient events? These questions blur the boundary between physics and philosophy in ways that would have seemed impossible to earlier generations of scientists. The investigation of pre-Big Bang conditions forces us to examine our most basic assumptions about time, causation, and the relationship between observer and observed. We find ourselves constructing theories where the act of cosmic observation might literally participate in creating the history being observed. This observer-participatory aspect of cosmology becomes even more intriguing when we consider the role of consciousness in quantum mechanics. Some interpretations suggest that conscious observation plays a crucial role in collapsing quantum superpositions into definite outcomes. If consciousness is indeed fundamental to quantum mechanics, then the emergence of conscious observers in our universe might have retroactively determined which pre-Big Bang superposition became actualized. In this view, the question of what came before the Big Bang cannot be separated from the question of why conscious observers eventually emerged to ask such questions. The pre-Big Bang state might have been selected from among infinite quantum possibilities, precisely because it led to the development of minds capable of contemplating cosmic origins. Consciousness and cosmos become co-evolutionary partners in a cosmic dance of mutual determination. Such ideas venture into territory where science approaches something almost mystical in its implications. Yet they emerge from rigorous mathematical analysis of quantum mechanics applied to cosmological scales. The strange loop between cosmic evolution and conscious observation appears to be built into the fundamental structure of physical law rather than representing some exotic philosophical speculation. But even as we explore these mind-bending possibilities, alternative approaches to pre-Big Bang physics continue to evolve in directions that offer different insights into cosmic origins. The holographic principle, derived from studies of black hole physics, suggests that all the information in any region of space can be encoded on its boundary. Applied to cosmology, this principle implies that our entire three-dimensional universe might be equivalent to information encoded on a two-dimensional surface at the cosmic boundary. If the holographic principle applies to pre-Big Bang physics, then what we interpret as the evolution of a three-dimensional cosmos might actually represent the dynamics of information on a timeless two-dimensional surface. The Big Bang wouldn't be an event in space and time, but rather a reorganization of information on this cosmic boundary, projected into our three-dimensional experience as temporal evolution. This holographic perspective radically alters our understanding of what it means for something to exist before the Big Bang. Instead of seeking events in a pre-Big Bang timeline, we would be investigating how information on the cosmic boundary encodes what appears to us as temporal sequence. The question becomes not what happened before, but how boundary information generates the appearance of cosmic history. The mathematics of holographic cosmology are extraordinarily abstract, involving concepts from string theory, quantum field theory, and information theory that push mathematical physics to its limits. Yet they offer tantalizing glimpses into possible solutions to some of cosmology's deepest puzzles. If our three-dimensional reality is indeed holographic, then the fine-tuning problems that plague traditional cosmology might dissolve into natural consequences of information-theoretic principles. These holographic approaches also suggest new ways of thinking about the multiverse. Instead of imagining infinite three-dimensional universes scattered throughout higher dimensional space, holographic cosmology envisions different universes as different information patterns encoded on the same cosmic boundary. The multiverse becomes not a collection of separate realities, but different interpretations of the same underlying information structure. This information-theoretic view of cosmic origins connects with cutting-edge research in quantum computation and artificial intelligence. Some theorists have proposed that the pre-Big Bang state might be understood as a cosmic computational process, with physical evolution representing the execution of some vast algorithm encoded in the fundamental structure of reality. If the universe is indeed a kind of cosmic computer, then the Big Bang might represent a phase transition in this computational process, a moment when the algorithm shifted from one mode of operation to another. The pre-Big Bang era would then be characterized not by particular physical conditions, but by the computational rules that govern cosmic information processing. This computational perspective on cosmology raises fascinating questions about the relationship between mathematical possibility and physical actuality. If physical evolution represents the execution of mathematical algorithms, then the laws of physics become programming languages that describe how cosmic computation unfolds. The question of what came before the Big Bang becomes a question about the deeper computational principles that determine which algorithms get executed in physical reality. But perhaps the most profound insight emerging from these diverse approaches to pre-Big Bang physics is how they reveal the inadequacy of our ordinary concepts when applied to ultimate origins. Whether we invoke eternal inflation, quantum bounces, higher dimensional collisions, quantum superposition, holographic encoding, or cosmic computation, we find ourselves pushed beyond familiar notions of time, space, and causation. Each theoretical framework requires us to expand our conceptual vocabulary, to develop new ways of thinking about existence that transcend the categories of everyday experience. The pre-Big Bang realm appears to be a territory where our most basic intuitions about reality break down, replaced by mathematical relationships that operate according to logic so alien that it challenges our capacity for comprehension. Yet within this conceptual chaos, patterns emerge that suggest deep connections between seemingly disparate aspects of reality. Quantum mechanics and general relativity, information theory and thermodynamics, consciousness and cosmic evolution, all appear to be facets of some more fundamental unity that we're only beginning to glimpse. The search for this underlying unity has led physicists to propose ever more ambitious theories of everything, mathematical frameworks that attempt to derive all known physics from a single set of principles. String theory represents the most developed example of such unification attempts, proposing that all particles and forces emerge from the vibrational modes of tiny one-dimensional objects in higher dimensional space. But even string theory, for all its mathematical elegance, cannot answer the ultimate question of why anything exists at all. It can describe how different forms of existence relate to each other, but it cannot explain why these particular mathematical relationships should be instantiated in physical reality, rather than remaining as abstract possibilities. This limitation points towards something profound about the nature of explanation itself. Every scientific theory operates by showing how observed phenomena follow from more fundamental principles, but this process of explanation must eventually terminate in assumptions that cannot themselves be explained within the same framework. The deepest questions about existence might be unanswerable, not because they're too difficult, but because they probe the foundations upon which all explanation must rest. Recognizing this limitation doesn't diminish the value of our investigations into pre-Big Bang physics. Even if we cannot achieve ultimate explanations, we can still discover profound truths about the structure of reality and our place within it. The journey toward understanding cosmic origins transforms our conception of existence in ways that enrich human culture and consciousness. The various theoretical approaches we've explored each contribute unique perspectives to this transformation. Eternal inflation reveals how local finitude can coexist with global infinity, teaching us that our cosmic neighborhood might be just one bubble in an endless ocean of creation. Quantum bounce models show how apparent endings can transform into new beginnings, suggesting that death and birth are more intimately connected than we might imagine. Higher dimensional scenarios demonstrate how familiar three-dimensional reality might be embedded within structures so vast that we can barely conceive them. Quantum superposition cosmologies reveal how definiteness might emerge from indefiniteness, how the sharp edges of observed reality might arise from the fuzzy quantum realm of pure possibility. Holographic principles suggest that the distinction between appearance and reality might be more subtle than we assume, with three-dimensional experience potentially emerging from two-dimensional information. And computational approaches to cosmology hint that the universe itself might be engaged in an ongoing process of self-calculation, with physical evolution representing the execution of cosmic algorithms. Each of these perspectives offers insights that extend far beyond technical cosmology into fundamental questions about meaning, purpose, and the nature of conscious existence. They suggest that we are not accidental byproducts of meaningless physical processes, but integral participants in cosmic evolution that transcends any simple distinction between mind and matter. The recursive nature of our investigation becomes increasingly apparent as we delve deeper into these mysteries. We are using consciousness to investigate the cosmic conditions that gave rise to consciousness. We are employing mathematical reasoning to explore the mathematical foundations of physical existence. We are utilizing the universe's capacity for self-awareness to probe the origins of that capacity. This strange loop between investigator and investigated suggests that the question of what came before the Big Bang might be intimately connected with the question of what it means for anything to be conscious of its own existence. The pre-Big Bang state might have contained not just the seeds of matter and energy, but the quantum information patterns that would eventually give rise to minds capable of cosmic contemplation. If consciousness represents a fundamental feature of cosmic evolution, rather than an accidental emergent property, then our investigation of cosmic origins becomes part of the cosmic story itself. Every insight we achieve, every theoretical breakthrough we accomplish, every moment of wonder we experience in contemplating these mysteries represents the universe coming to know itself through the conscious minds it has somehow managed to create. This perspective transforms our understanding of what it means to be human in a cosmic context. We are not separate from the universe, observing it from outside, but rather expressions of the universe's inherent tendency towards self-organization and self-awareness. Our curiosity about cosmic origins reflects the cosmos investigating its own foundations through the remarkable phenomenon of conscious inquiry. The implications ripple through every aspect of human existence, from our sense of meaning and purpose to our understanding of mortality and transcendence. If we are indeed cosmic phenomena rather than cosmic accidents, then our brief existence participates in something far grander and more significant than individual biological survival. Yet even as we contemplate these profound connections between consciousness and cosmos, we must remain humble about the vast territories that remain unexplored. The question of what came before the Big Bang has led us into theoretical realms that stretch human comprehension to its limits, revealing as much about the boundaries of knowledge as about the structure of reality. The various frameworks we've examined represent humanity's best current attempts to push beyond these boundaries, to extend the reach of scientific understanding into territories that previous generations would have considered forever beyond human comprehension. Yet each new insight reveals new mysteries, new questions that we hadn't even known how to ask. This endless deepening of mystery might be the most important lesson emerging from our investigation. Rather than approaching some final understanding of cosmic origins, we seem to be discovering that reality is far stranger, more subtle, and more wonderful than we ever imagined. Each theoretical breakthrough opens new territories for exploration, new dimensions of mystery that invite further investigation. Perhaps this is as it should be, in a universe capable of giving rise to conscious inquiry. If reality were simple enough to be completely understood by finite minds, it might be too impoverished to generate the rich complexity that makes consciousness possible. The apparent inexhaustibility of cosmic mystery might be intimately connected with the universe's capacity to create minds capable of experiencing wonder and pursuing understanding. The question of what came before the Big Bang thus becomes not just a scientific puzzle, but a gateway into the deepest mysteries of existence itself. It connects the largest scales of cosmic evolution with the most intimate aspects of human consciousness, revealing threads of connection that weave through every level of reality, from quantum fields to conscious experience. As we continue this extraordinary journey of discovery, we carry with us the recognition that we are exploring territories where science and philosophy, mathematics and meaning, cosmic evolution, and conscious awareness converge in ways that transform our understanding of what it means to exist. The investigation itself becomes a form of cosmic meditation, an exploration of the deepest connections between mind and reality. The pre-Big Bang realm, whatever it was, contained within its quantum structure all the possibilities that would eventually unfold into our current universe, with its galaxies and stars, its planets and life, its conscious minds capable of contemplating their own cosmic origins. In seeking to understand that primordial state, we participate in the universe's ongoing process of self-discovery, using the gift of consciousness to illuminate the mystery of existence itself. The dance between possibility and actuality reveals itself most clearly when we consider how quantum mechanics might operate at cosmic scales. In our everyday experience, objects exist in definite states with precise locations and properties. But at the quantum level, particles exist in fuzzy clouds of probability until something forces them to choose a specific configuration. Some cosmologists have proposed that the pre-Big Bang state operated according to these same quantum principles, but magnified to encompass the entire cosmos. Imagine reality before the Big Bang as an infinite ocean of pure potential, where every conceivable cosmic configuration existed simultaneously in quantum superposition. No single timeline, no definite sequence of events, just an endless web of interconnected possibilities waiting for something to collapse them into actuality. The Big Bang itself might have been that moment of cosmic measurement, the universe choosing one path from among infinite alternatives. This quantum view of cosmic origins challenges our most basic assumptions about the nature of time and history. If the pre-Big Bang state contained all possibilities simultaneously, then asking what specific conditions existed becomes as meaningless as asking which path a particle took before we measured its position. There was no single before, but rather a ghostly ensemble of every conceivable before, each weighted by probability amplitudes that describe the likelihood of different cosmic outcomes. The mathematics that describe such quantum superposition cosmologies operate in abstract spaces with more dimensions than we can visualize. They speak of wave functions that span infinite dimensional configuration spaces, of probability amplitudes that evolve according to equations so complex they require the most powerful computers to solve even simplified versions. Yet within this mathematical complexity, patterns emerge that match our observations with startling precision. But quantum superposition at cosmic scales raises puzzling questions about the role of observation in determining reality. In standard quantum mechanics, the act of measurement plays a crucial role in collapsing quantum possibilities into definite outcomes. If the early universe existed in quantum superposition, what caused that superposition to collapse into the specific cosmos we observe today? Some theorists have proposed that consciousness itself might play a fundamental role in this cosmic collapse. Not in any mystical sense, but through the deep connection between observation and reality that quantum mechanics reveals the emergence of conscious observers, billions of years after the Big Bang, might have retroactively determined which quantum superposition became actualized, creating a strange loop where the future influences the past. This observer participatory universe suggests that the question of what came before the Big Bang cannot be separated from the question of why conscious beings eventually emerged to contemplate cosmic origins. We might exist not despite the apparent fine-tuning of physical constants, but because our existence was necessary to collapse the quantum superposition of pre-Big Bang possibilities into a reality capable of supporting conscious inquiry. Yet even as we explore these mind-bending quantum scenarios, alternative approaches to pre-Big Bang physics continue to evolve in directions that offer radically different perspectives on cosmic origins. String theory, with its vision of reality composed of tiny vibrating filaments in higher dimensional spaces, suggests that our familiar universe might be just one membrane floating in a vast extra-dimensional realm. In these string-theoretic frameworks, our Big Bang might have resulted from a collision between such membranes in hyperspace picture 2 cosmic sheets, each carrying its own three-dimensional reality, slowly approaching each other through dimensions we cannot perceive. When these brains finally collide, the energy of impact creates the extreme conditions we associate with cosmic genesis. But unlike traditional Big Bang models that require a singular beginning, these brain collision scenarios suggest an eternal process of cosmic creation. The membranes don't disappear after collision, but rather bounce apart, drift through higher dimensional space, and eventually approach each other again for another cosmic encounter. Each collision generates a new universe, while the brains themselves continue their endless dance through dimensions beyond our direct experience. The mathematical beauty of these higher dimensional models lies in their ability to explain many puzzling features of our cosmos without requiring the infinite densities that plague traditional singularity-based theories. Instead of everything emerging from a point of mathematical impossibility, brain collisions create finite but extreme conditions that naturally evolve into expanding universes. These cyclical brain scenarios also address one of the deepest puzzles in cosmology: why the fundamental constants of physics seem so perfectly calibrated for the existence of complex structures and conscious life. If universes are created through eternal cycles of brain collisions, each cycle might explore slightly different combinations of physical laws and initial conditions. Most experiments might produce sterile realities incapable of generating complexity, but occasionally the parameters align in ways that allow for stars, planets, and minds capable of contemplating their own existence. This evolutionary view of cosmic law suggests that our universe represents not a random accident, but a kind of cosmic achievement, the result of an ongoing process that gradually optimizes reality for complexity and consciousness. The pre-Big Bang state becomes not a single condition, but an eternal exploration of possibility, with each cosmic cycle testing new combinations of physical principles. But the implications extend even further when we consider how information might propagate across these cosmic cycles. Recent research suggests that quantum information possesses a kind of indestructibility that persists even under the most extreme conditions. If this is correct, then traces of previous cosmic cycles might survive the violent conditions of brain collisions, carrying forward subtle patterns that influence the evolution of subsequent universes. This cosmic memory effect would mean that our current universe might carry within its deepest structure the faint echoes of countless previous cosmic experiments. The particular mix of matter and energy we observe, the specific values of fundamental constants, even the initial fluctuations that seeded galaxy formation might reflect accumulated wisdom from an endless series of cosmic iterations. The search for such trans-cyclical signatures represents one of the most ambitious programs in theoretical physics. Researchers are developing increasingly sophisticated techniques to extract ancient signals from current observations, looking for patterns in the cosmic microwave background that might preserve information from pre-Big Bang epochs. Every quantum fluctuation, every gravitational wave, every subtle correlation in cosmic structure might carry encrypted messages from previous cosmic incarnations. But as we develop these extraordinary investigative capabilities, we encounter fundamental questions about the nature of cosmic identity and continuity. If the universe undergoes eternal cycles of destruction and rebirth, with information patterns persisting across transitions, what does it mean for our cosmic epoch to be unique? Are we living in an unprecedented chapter of cosmic evolution? Or have there been previous versions of reality so similar to ours that the distinction becomes meaningless? These questions probe the relationship between repetition and uniqueness in ways that challenge our most basic concepts of identity and significance. The mathematics suggests that while overall patterns might repeat across cosmic cycles, the details could vary in ways that make each universe both familiar and utterly unique, like variations on an infinite cosmic theme. Some theorists have pushed these ideas even further, proposing that the boundaries between different cosmic cycles might not be as sharp as we imagine. Instead of discrete transitions from one universe to another, reality might exist in a state of continuous transformation, with cosmic evolution representing an ongoing flow rather than a series of separate events. This flowing cosmos model suggests that asking what came before the Big Bang is like asking about the source of a river. There's no single beginning point, but rather a continuous process of cosmic becoming that extends infinitely in all temporal directions. Our Big Bang becomes not an origin, but a particular moment in an eternal process of cosmic self-transformation. The mathematical frameworks that describe these flowing cosmologies operate with concepts of time that stretch far beyond our everyday experience. They speak of temporal dimensions that can branch and merge, of causal relationships that loop back on themselves, of cosmic evolution that proceeds according to principles so alien to human intuition that we can approach them only through abstract mathematical reasoning. Yet within these strange temporal geometries, patterns emerge that connect the smallest quantum scales with the largest cosmic structures. The same principles that govern the behavior of subatomic particles also shape the evolution of universe-spanning processes, revealing deep unities that suggest all of reality operates according to a single underlying logic. This unity becomes even more apparent when we consider how consciousness fits into these cosmic scenarios. Rather than being an accidental byproduct of complex chemistry, awareness might represent a fundamental aspect of cosmic evolution, as basic to reality as matter and energy. The pre-Big Bang state might have contained not just the quantum seeds of particles and forces, but the information patterns that would eventually give rise to minds capable of cosmic contemplation. If consciousness is indeed woven into the fabric of reality at the deepest level, then our investigation of cosmic origins becomes more than just scientific inquiry. It becomes a form of cosmic self-exploration, the universe using its own evolved capacity for awareness to investigate the foundations of that capacity. Every question we ask about pre-Big Bang conditions participates in reality's ongoing process of self-discovery. This recursive relationship between cosmic evolution and conscious inquiry suggests that the mystery of what came before the Big Bang might be intimately connected with the mystery of why anything is conscious of its own existence. The pre-Big Bang realm might have been characterized not just by particular physical conditions, but by the potential for reality to become aware of itself through the eventual emergence of questioning minds. But consciousness in cosmic evolution raises profound questions about the nature of experience and observation at the deepest levels of reality. If awareness plays a fundamental role in collapsing quantum possibilities into definite outcomes, then the pre-Big Bang superposition might have persisted until the first conscious observers emerged to witness and thereby determine cosmic history. This participatory view of cosmic evolution suggests that we are not passive observers of a pre-existing reality, but active participants in the ongoing creation of that reality. Our investigation of pre-Big Bang physics doesn't just reveal what happened in the distant past, but helps determine what that past becomes through the act of investigation itself. The implications ripple through our understanding of scientific objectivity and the relationship between observer and observed. Traditional science assumes a clear separation between the investigator and the phenomena being studied. But at the deepest levels of cosmic inquiry, this separation dissolves into something more subtle and participatory, where the act of investigation becomes part of the cosmic story being investigated. This participatory aspect of cosmological research becomes even more intriguing when we consider the role of mathematical beauty in guiding theoretical development. Many of the most successful theories in physics have been discovered not through experimental observation, but through the pursuit of mathematical elegance and symmetry. Researchers follow equations toward conclusions that often seem to transcend human imagination, as if mathematics itself were revealing the hidden structure of reality. The pre-Big Bang theories we've explored all share this quality of mathematical beauty. Whether describing quantum superposition cosmologies, higher dimensional brane collisions, or cyclical cosmic evolution, the equations exhibit symmetries and elegances that seem to point beyond themselves toward deeper truths about the nature of existence. This connection between mathematical beauty and physical truth suggests that the pre-Big Bang realm might be characterized not just by particular conditions or processes, but by the abstract relationships that govern how possibilities become actualities. The deepest level of cosmic reality might be mathematical in nature, with physical existence emerging as particular solutions to equations that describe the structure of possibility itself. But mathematics, for all its power to describe relationships and predict outcomes, cannot explain why any particular set of equations should be instantiated in physical reality. Why should the abstract patterns described by quantum field theory or general relativity correspond to actual events in space-time? This remains one of the most profound mysteries connecting cosmic origins with the foundations of mathematical knowledge. Some philosophers and physicists have proposed that mathematics itself might be the ultimate reality, with physical universes emerging as specific interpretations of abstract mathematical structures. In this view, the question of what came before the Big Bang becomes a question about the relationship between mathematical possibility and physical actuality, between the realm of pure form and the domain of concrete existence. This mathematical universe hypothesis suggests that all possible mathematical structures exist in some sense, with conscious observers like ourselves finding themselves embedded in those structures complex enough to support awareness and inquiry. The pre-Big Bang state would then represent not a physical condition, but a mathematical relationship, a pattern of abstract connections that inevitably gives rise to the appearance of temporal evolution and cosmic history. But even this most abstract approach to cosmic origins cannot escape the fundamental puzzle of why anything should exist at all. Mathematical structures might describe how different aspects of reality relate to each other, but they cannot explain why these relationships should be instantiated rather than remaining as pure abstractions. The question of absolute existence transcends any particular theoretical framework, pointing toward mysteries that might lie forever beyond the reach of human comprehension. Yet the pursuit of these ultimate questions continues to drive scientific research in directions that expand our understanding of what it means to exist. Each new theoretical framework, each mathematical breakthrough, each conceptual innovation contributes to an ever-deepening appreciation for the profound mystery of existence itself. The various approaches to pre-Big Bang physics we've explored each reveal different facets of this mystery. Quantum superposition cosmologies show how definiteness might emerge from indefiniteness, how the sharp boundaries of observed reality might arise from fuzzy quantum possibilities. Higher dimensional scenarios demonstrate how familiar experience might be embedded within structures so vast and complex that we can barely begin to imagine them. Cyclical models reveal how endings and beginnings might be more intimately connected than we assume, with each cosmic death containing the seeds of cosmic rebirth. Mathematical universe hypotheses suggest that the distinction between abstract possibility and concrete actuality might be more subtle than common sense supposes. Each perspective contributes unique insights while pointing towards something that transcends any single theoretical approach. The pre-Big Bang realm appears to be a domain where our familiar concepts of time, space, and causation break down, replaced by relationships so fundamental that they shape the very categories through which we must think about existence. This conceptual breakdown doesn't represent a failure of human understanding, but rather reveals the extraordinary nature of what we're attempting to comprehend. We are finite minds embedded within the very reality we're trying to understand, using tools evolved for navigating everyday experience to probe the ultimate foundations of existence itself. The recursive nature of this investigation creates strange loops where the inquiry becomes part of what's being inquired into. We are the universe investigating its own origins, temporary patterns of matter and energy that have achieved the remarkable capacity for cosmic self-reflection. Every question we ask about pre-Big Bang conditions represents reality probing its own foundations through the conscious minds it has somehow managed to create. This self-referential aspect of cosmological inquiry adds layers of meaning that extend far beyond technical scientific questions into fundamental issues of purpose and significance. If consciousness represents a fundamental feature of cosmic evolution, rather than an accidental byproduct, then our capacity to contemplate cosmic origins participates in something far grander than individual biological existence. The investigation of what came before the Big Bang becomes not just an attempt to understand distant events, but a form of cosmic meditation, an exploration of the deepest connections between mind and reality. Through conscious inquiry into cosmic origins, we participate in the universe's ongoing process of self-discovery, contributing to reality's evolving understanding of its own nature. As we continue this extraordinary journey toward the deepest mysteries of existence, we carry with us the recognition that we are exploring territories where science and philosophy, mathematics and meaning, cosmic evolution, and conscious awareness converge in ways that transform our understanding of what it means to be conscious observers in a mysterious universe. The question of what came before the Big Bang may never receive a final definitive answer, but the investigation itself reveals profound truths about the nature of reality and our place within it. Each theoretical breakthrough, each conceptual innovation, each moment of wonder experienced in contemplating these cosmic mysteries represents the universe coming to know itself through the remarkable phenomenon of conscious inquiry. We find ourselves at the edge of the ultimate mystery, where the investigation of cosmic origins becomes indistinguishable from the exploration of consciousness itself. The pre-Big Bang realm, whatever it was, contained within its quantum structure all the possibilities that would eventually unfold into minds capable of asking questions about their own cosmic heritage. In seeking to understand that primordial state, we participate in an ongoing cosmic dialogue between reality and awareness, between the universe's capacity for self-organization and its drive towards self-comprehension. The mystery deepens with every answer we discover, revealing new dimensions of wonder that invite further exploration into the heart of existence itself. And yet, as we stand at this threshold between the known and unknowable, perhaps the most remarkable discovery is not any particular theory about what preceded our cosmic beginning, but rather the profound realization that we exist at all to contemplate such questions. In the vast expanse of possibility, in the infinite ocean of potential realities, somehow the universe has organized itself in such a way that portions of it have become capable of wonder, of curiosity, of the deep longing to understand origins. This capacity for cosmic contemplation emerges from the same processes we seek to understand. The atoms that compose our thoughts were forged in stellar furnaces billions of years ago. The neural patterns that generate our questions about pre-Big Bang physics operate according to the same quantum mechanical principles that might have governed the primordial state itself. We are not separate from the mystery we investigate, but intimately woven into its very fabric. Consider the extraordinary chain of emergence that connects the deepest theoretical physics with this moment of quiet reflection. Whatever existed before the Big Bang, whether quantum foam or colliding brains or eternal inflation or something beyond our current imagination, it contained within its structure the potential for increasing complexity. From that primordial state emerged the first particles, then atoms, then molecules, then the intricate chemistry that eventually gave rise to life, consciousness, and the remarkable phenomenon of minds capable of mathematical reasoning. This emergence of complexity from simplicity represents one of the most profound mysteries in all of science. How does a universe that begins in apparent chaos or uniformity give rise to the rich tapestry of structure we observe today? How do unconscious processes generate conscious experience? How does matter organize itself into patterns capable of contemplating their own existence? The theories we've explored offer glimpses into these deeper questions about cosmic evolution and the nature of emergence itself. If our universe arose from quantum fluctuations in a pre-Big Bang vacuum, then even apparent nothingness possesses a hidden richness, a potential for spontaneous organization that defies our everyday understanding of emptiness. The quantum vacuum reveals itself not as mere absence, but as a dynamic medium seething with possibility. If reality emerged from collisions between higher dimensional membranes, then our familiar three-dimensional experience represents just the surface of a far more complex underlying structure. The emergence of consciousness within such a framework suggests that awareness itself might be a fundamental feature of higher dimensional physics, manifesting in our cosmic domain as the remarkable phenomenon of minds capable of contemplating their own origins. And if the universe undergoes eternal cycles of contraction and expansion, then consciousness becomes not a temporary accident, but a recurring theme in cosmic evolution. Each cycle might explore different pathways toward complexity and awareness, with our particular epoch representing one variation in an infinite cosmic symphony of emergent consciousness. These perspectives transform our understanding of what it means to be human in a cosmic context. We are not isolated accidents clinging to a tiny planet in an indifferent universe, but rather expressions of the cosmos itself, temporary arrangements of matter and energy through which reality investigates its own foundations. Our curiosity about cosmic origins reflects the universe's inherent drive towards self-understanding. This cosmic perspective reveals something profound about the nature of scientific inquiry itself. When we develop theories about pre-Big Bang physics, we are not merely collecting information about distant events, but participating in the universe's ongoing process of self-discovery. Every equation we derive, every theoretical insight we achieve, every moment of wonder we experience represents reality coming to know itself through the conscious minds it has created. The recursive nature of this investigation creates a strange and beautiful symmetry. The universe that emerged from whatever pre-Big Bang conditions existed has evolved to the point where it can contemplate its own origins. Matter has organized itself into brains capable of mathematical reasoning about the quantum processes that gave rise to matter itself. Energy has configured itself into neural networks that can theorize about the energetic conditions that preceded their existence. But this self-referential aspect of cosmological inquiry also reveals the profound limitations we face in seeking ultimate explanations. Every theory we construct operates within the conceptual framework provided by the very universe we're trying to understand. We cannot step outside reality to observe it from some neutral vantage point. We can only investigate the cosmos from within, using tools and concepts that are themselves products of cosmic evolution. This limitation doesn't invalidate our investigations, but rather highlights their unique character. We find ourselves in the remarkable position of being the universe studying itself, using its own evolved complexity to probe the conditions that gave rise to that complexity. The investigation becomes a cosmic mirror, reflecting not just the structure of reality, but the nature of consciousness embedded within that reality. As we've seen throughout our exploration, each approach to pre-Big Bang physics reveals as much about the nature of inquiry as about cosmic origins themselves. Quantum superposition cosmologies show us how definiteness emerges from indefiniteness, but they also reveal how observation participates in creating the reality being observed. Higher dimensional theories demonstrate the vast complexity that might underlie familiar experience, while simultaneously showing how limited our direct access to that complexity must remain. Cyclical models suggest that endings and beginnings might be more intimately connected than we assume, but they also raise profound questions about identity and uniqueness across cosmic cycles. If the universe repeats its evolutionary patterns, what makes any particular cycle significant? If consciousness emerges repeatedly through cosmic time, what distinguishes our awareness from its countless predecessors and successors? These questions probe the relationship between cosmic evolution and meaning in ways that extend far beyond technical physics, into fundamental issues of purpose and significance. If we are part of an eternal cosmic process rather than unique accidents, does this diminish or enhance the meaning of our existence? If consciousness represents a recurring theme in cosmic evolution, rather than an unprecedented emergence, does this make our awareness more or less remarkable? Perhaps the answer lies not in choosing between these alternatives, but in recognizing how they point towards something deeper about the nature of existence itself. The universe appears to be structured in such a way that complexity and consciousness emerge naturally from simpler beginnings, whether through single evolutionary sequences or repeated cycles or parallel developments in multiple cosmic domains. This natural tendency toward increasing complexity and awareness suggests that mind and matter, consciousness and cosmos, are not separate entities that accidentally encounter each other, but rather different aspects of a single underlying reality. The pre-Big Bang state, whatever it was, contained within its structure not just the seeds of particles and forces, but the information patterns that would eventually give rise to minds capable of cosmic contemplation. This perspective transforms our understanding of the relationship between science and meaning. Rather than revealing a cold, mechanical universe indifferent to consciousness and purpose, our investigation of pre-Big Bang physics unveils a reality that appears to be inherently creative, naturally generating the complexity and awareness that makes scientific inquiry possible. The mathematical beauty that guides our theoretical investigations hints at deeper connections between mind and cosmos than materialist philosophy typically acknowledges. The fact that abstract mathematical relationships correspond so precisely to physical phenomena suggests that the universe operates according to principles that transcend any simple distinction between subjective thought and objective reality. When we discover elegant equations that describe cosmic evolution, we are not merely imposing human patterns on indifferent matter, but rather uncovering relationships that exist at the deepest levels of reality itself. The mathematics that describes pre-Big Bang scenarios possesses a kind of independent existence that constrains what kinds of universes are possible and what kinds of consciousness can emerge within them. This mathematical structure of reality becomes even more mysterious when we consider how it connects with the emergence of minds capable of discovering it. The same cosmic processes that gave rise to conscious observers also created brains capable of understanding the mathematical relationships governing those processes. The universe has organized itself in such a way that it can comprehend its own organization. But mathematics alone cannot explain why any particular set of relationships should be instantiated in physical reality rather than remaining as pure abstractions. The question of why there is something rather than nothing transcends any specific theoretical framework, pointing toward mysteries that might forever remain beyond the reach of finite minds. Yet, the pursuit of these ultimate questions continues to enrich human consciousness and culture in ways that extend far beyond technical scientific applications. Each new insight into cosmic origins expands our conception of what it means to exist, revealing connections between the smallest quantum scales and the largest cosmic structures, between the earliest moments of time and the emergence of minds capable of contemplating temporality itself. The various theoretical approaches to pre-Big Bang physics we've explored each contribute unique perspectives to this expanding vision of reality. They show us a universe far stranger and more wonderful than common sense would suggest, operating according to principles that challenge our deepest intuitions about time, space, and causation, while simultaneously revealing profound unities that connect all aspects of existence. Whether through eternal inflation or quantum bounces, colliding brains or cyclical evolution, mathematical universe hypotheses or consciousness participatory scenarios, Each framework opens new territories for exploration, while pointing towards something that transcends any particular theoretical approach. The mystery deepens with every answer we discover, revealing new dimensions of wonder that invite further investigation. This endless deepening of mystery might be the most important lesson emerging from our journey into pre-Big Bang physics. Rather than approaching some final understanding of cosmic origins, we seem to be discovering that reality is inexhaustibly rich, possessing depths of complexity and beauty that exceed any finite capacity for comprehension. Perhaps this inexhaustibility is intimately connected with the universe's ability to generate conscious minds capable of experiencing wonder and pursuing understanding. If reality were simple enough to be completely grasped by finite intelligence, it might be too impoverished to give rise to the rich complexity that makes consciousness possible. The apparent infinity of cosmic mystery thus becomes not an obstacle to understanding, but a necessary condition for the existence of minds capable of appreciating mystery itself. We find ourselves in a universe that is simultaneously comprehensible and incomprehensible, knowable and unknowable, familiar and utterly strange. This paradoxical nature of cosmic reality reflects something fundamental about the relationship between finite consciousness and infinite existence. We are temporary patterns of matter and energy that have achieved the remarkable capacity to contemplate infinity, limited minds embedded within unlimited reality, mortal beings capable of touching something eternal through the pursuit of truth and beauty. The question of what came before the Big Bang thus becomes not just a scientific puzzle, but a gateway into the deepest mysteries of existence itself. It connects the largest scales of cosmic evolution with the most intimate aspects of conscious experience, revealing threads of meaning that weave through every level of reality, from quantum fields to questioning minds. As our exploration draws toward its conclusion, we find ourselves not with final answers, but with a profound appreciation for the magnificent mystery of existence itself. The pre-Big Bang realm, whatever it was, contained within its quantum structure all the possibilities that have unfolded into our current universe, with its galaxies and stars, its planets and life, its conscious minds capable of wonder and inquiry. In seeking to understand that primordial state, we participate in the universe's ongoing journey towards self-knowledge, using the gift of consciousness to illuminate the mystery of consciousness itself. Every question we ask about cosmic origins represents reality probing its own foundations through the aware beings it has somehow created. The investigation becomes a form of cosmic dialogue, a conversation between the universe's capacity for self-organization and its drive towards self-understanding. We are both the questioners and part of what is being questioned, both the investigators and integral aspects of what is being investigated. This participatory quality of cosmological inquiry reveals something beautiful about our place in the grand scheme of existence. We are not outside observers studying an alien universe, but rather the cosmos awakening to itself, temporary expressions of reality's inherent tendency toward complexity and consciousness. The mystery of what came before the Big Bang may never be completely resolved, but the investigation itself transforms our understanding of what it means to be conscious beings in a mysterious cosmos. Through our questioning and wondering, through our mathematical reasoning and theoretical speculation, through our moments of insight and experiences of awe, we participate in something far grander than individual existence. We are the universe, contemplating its own origins. Cosmic evolution becomes self-aware, the mysterious investigating mystery itself. And in that recognition, we touch something profound about the nature of existence that transcends any particular theory about what preceded our cosmic beginning. The questions remain open, the mystery continues to deepen, and consciousness continues its eternal dance with the cosmos that gave it birth. In this dance, we find not final answers but something perhaps more valuable, an ever-expanding sense of wonder at the magnificent improbability and profound beauty of existence itself. Through all these theoretical explorations, we find ourselves returning again and again to a fundamental question that lies beneath every equation, every model, every elegant mathematical framework. Why should any of this exist at all? Why should there be quantum fields capable of fluctuation, higher dimensions through which brains can collide, cycles of cosmic evolution, or mathematical relationships that somehow give rise to physical reality? This question pushes us beyond the boundaries of what science can typically address. We can describe how things work, map the relationships between different phenomena, predict the outcomes of cosmic processes. But the deeper question of why anything should work at all, why there should be laws and patterns and possibilities rather than pure nothingness, seems to hover just beyond the reach of any theoretical framework. Perhaps this limitation points to something profound about the nature of existence itself. Every explanation we construct must assume certain foundations, certain starting points that cannot themselves be explained within the same framework. The search for ultimate origins might be chasing something that cannot exist in principle, an explanation that would somehow transcend the need for assumptions or foundations. Yet this apparent limitation doesn't diminish the profound transformation that our investigation has wrought in our understanding of reality. Even if we cannot achieve final explanations, we have discovered truths about the cosmos that would have seemed impossible to earlier generations. We have learned that time itself might be emergent rather than fundamental, that space could be quantized at the smallest scales, that our entire observable universe might be just one bubble in an infinite ocean of cosmic creation. These insights reveal a reality far stranger and more wonderful than our ancestors could have imagined. The solid, predictable world of everyday experience dissolves into quantum foam and probability waves, higher dimensional geometries and cyclical eternities. The universe becomes not a machine but a living process, not a static container, but a dynamic unfolding of possibility into actuality. This transformation in our cosmic vision has profound implications for how we understand our own existence. If the universe is indeed structured as these theories suggest, then consciousness emerges not as an accident, but as a natural consequence of cosmic evolution. Mind and matter reveal themselves as different aspects of a single underlying reality, with awareness representing not an intrusion into physical processes, but their natural flowering into self-reflection. The recursive nature of our investigation becomes even more remarkable when viewed from this perspective. We are not separate beings studying an alien cosmos, but rather expressions of the universe's inherent tendency towards self-organization and self-awareness. Our curiosity about pre-Big Bang conditions reflects the cosmos probing its own foundations through the conscious minds it has created. This participatory quality of cosmic inquiry suggests that the question of what came before the Big Bang is intimately connected with the question of why there are beings capable of asking such questions. The pre-Big Bang state, whatever it was, contained within its structure not just the seeds of matter and energy, but the information patterns that would eventually give rise to minds capable of cosmic contemplation. Every moment of wonder we experience in contemplating these mysteries, every insight we achieve through mathematical reasoning, every theoretical breakthrough that expands our understanding, represents the universe coming to know itself through the remarkable phenomenon of conscious inquiry. The investigation becomes a cosmic mirror, reflecting not just the structure of reality, but the nature of the consciousness embedded within it. But as we stand at this threshold between the known and unknowable, we encounter something that might be even more profound than any specific theory about cosmic origins. We discover that the capacity to ask ultimate questions, to experience wonder in the face of mystery, to pursue truth despite its apparent elusiveness, represents one of the most remarkable features of existence itself in a cosmos that began in simplicity, whether as quantum fluctuations or colliding brains or cyclical evolution or pure mathematical possibility. Somehow complexity has emerged that can contemplate its own emergence. Matter has organized itself into patterns capable of understanding matter. Energy has configured itself into neural networks that can theorize about energy. Time has given rise to minds that can question the nature of time itself. This emergence of self-aware complexity from simpler beginnings might be the most extraordinary fact about reality. It suggests that the universe possesses an inherent creativity, a natural tendency toward increasing organization and consciousness that operates regardless of the specific mechanisms involved. Whether through single evolutionary sequences or repeated cycles, or parallel developments across multiple cosmic domains, reality seems naturally drawn toward states that can contemplate their own existence. The mathematical beauty that guides our theoretical investigations hints at even deeper connections between mind and cosmos. The fact that abstract relationships correspond so precisely to physical phenomena suggests that the boundary between subjective thought and objective reality might be more porous than we typically assume. When we discover elegant equations describing cosmic evolution, we might be uncovering not just human interpretations of natural patterns, but fundamental structures that exist at the deepest levels of reality itself. This mathematical structure of existence becomes particularly mysterious when we consider how it connects with the emergence of minds capable of discovering it. The same cosmic processes that gave rise to conscious observers also created brains capable of understanding the mathematical principles governing those processes. The universe has organized itself in such a way that it can comprehend its own organization through the conscious beings it has produced. Yet mathematics alone cannot bridge the gap between abstract possibility and concrete existence. The question of why particular mathematical relationships should be instantiated in physical reality rather than remaining as pure abstractions continues to hover at the edges of our understanding. We can describe how different forms of existence relate to each other, but we cannot fully explain why these relationships should manifest as actual rather than merely possible. And so we find ourselves at the end of our cosmic journey, having traveled through theories that stretch the very fabric of imagination itself. We've explored quantum foam and colliding brains, eternal inflation and cyclical universes, each offering glimpses into the profound mystery of what might have existed before our beginning. Perhaps the most remarkable discovery is not any single answer, but the recognition that we exist at all to contemplate such questions. In this moment of quiet reflection, as you prepare to drift into sleep, remember that you are part of the very mystery we've been exploring. Sweet dreams, fellow traveler in the cosmic story. The universe continues its ancient dance around you, and you are part of that dance, now and always.